Hello, everyone. Uh, Originally, I thought I could say everything that I thought was important about this topic in one lecture, but it turns out I need to split it into two parts. So, this first part will introduce some concepts about Bayesian inference and introduce simple linear regression model. And then in the second part, we will be using that simple linear regression model to go into Bayesian computation. Right? So the outline of this component, first, I want to talk a little bit about the origins of Bayesian inference, introduce a simple linear regression example, and provide some comparison between frequentist versus Bayesian inference. So the history of Bayesian inference is actually kind of interesting. Bayes' theorem, quote unquote, was first published in an essay, or at least derived from what was published in an essay in 1763 that was actually submitted posthumously by his friend, Mr. Price. And I included this link to this paper I thought was an interesting description of the history of what we call Bayesian inference, which is more modern than this. Um, but I was curious about where Bayes' rule comes from, so I looked through this old essay, and the closest thing that made sense to me was this statement. The probability that two subsequent events will both happen is compounded to the probability of the first and the probability of the second on supposition of the first. So basically, this is kind of saying the joint probability that A is successful and B is successful is the probability of A is successful times the probability that B is successful, assuming A has been. And I found this fairly intuitive. And by the same logic, the other way holds true. Probability of B times probability of A, assuming B has happened. So since these are equivalent, you can say that these two sides of the equations are equal. And with some minor rearranging, you get Bayes' rule, which should be quite familiar to you, or at least it will be very familiar to you. And one more step in what makes Bayes' rule so innovative is that we extend this two event scenario to a general theorem that you can predict any kind of unknown or unobservable parameter using known or observable data and some kind of prior understanding about those parameters. And this idea was so powerful that Bayes' friend Richard Price thought it confirmed the existence of the deity, which I think is maybe taking it a little far, but that's a fresh take on Bayes' rule. This was from the original submission. Um, so this just saying parameters and data is a very abstract concept. So I just want to ground us a little bit in agroecology and sustainability science. So we're often trying to estimate some kind of unknown or unobservable parameter from data. For example, if we're interested in disease resistance, this is an abstract concept. We can only measure it based on the occurrence and severity of disease. Similarly, drought resilience, we might are limited to performance or yield in wet and dry years. And perhaps we're interested in how observable phenomena affect each other. For example, what is the effect of some management practice on soil health? We have to observe the management practice and the soil health indicators. So I should say that even though I'm introducing this in a Bayesian context, the idea of estimating unknown parameters from data is not uniquely Bayesian. That's just statistical inference in general. Um, so now I'm going to introduce the simple linear regression example that we'll build on as we go. So first, I want to set up a model just that we'll build on, and then but I want to introduce this, calling back to some of the other concepts of telling a data story based on science and thinking about the causes and effects. So let's just think about a simple system. We're interested in rain-fed rice yield. So we have a data story of how these yield data came to exist. Let's say rain-fed rice is grown on one farm under optimal temperature, soil, and management conditions. Rice is planted and harvested once per year every year, so there's no carryover effects. Every year is independent of the other. Rice yield is limited by water availability through rainfall. So I've added rainfall now to our um, causal conceptual model. And then rice yield also varies for random reasons unrelated to rainfall. So I'm just putting this as a general random reasons. So we could express that the yield that we're interested in is some function of rainfall and randomness. Um, so now if we use this to build our statistical model, a good first step will be plotting our data. So I've just put yield and rainfall on an XY axis. And I should mention that, in when we're measuring the data, often we're using units that make sense for a phenomenon of interest, but they may be at scales and units that don't necessarily work well for building statistical models. So here, what I've done is some data processing that's fairly typical, centering the variable and dividing by standard deviation, so you get common unitless scale. So that's why the scale looks like it does here. So based on this, we could say that these two represent random variables, which we can describe as x and y, and then a change in x, which is our predictor variable, is associated with a change in y. In this case, we might even say it causes a change in y due to our science knowledge. Um, so this whole system could be represented by a line that we draw through these points. So this is our basic linear regression model with one predictor, a response, and then an intercept and a slope describing this line, and then some error term that describes scatter around the line. So I've chosen to model error with simple Gaussian noise. So this just means that if you subtracted off the line from the points, you would get a bell curve centered at 0. So that's how I'm expressing this. So normal distribution with a mean of 0 and a variance of 1 over tau. So in this example, I'm going to be expressing the precision instead of the variance, but it's just the reciprocal, um, and becomes a little bit more convenient with the math and the sampling. All right. So we now have our data, x and y, and we have a set of three parameters that we're going to be trying to estimate. And these parameters describe both the effect of rainfall on yield and the effect of randomness on yield. We can think of that. All right, so I just want to spend a little time comparing frequentist versus Bayesian inference, just the high points. So, general overview. For frequentist inference, our focus is on estimating parameter values that best explain the data. So we just want to find one value of a parameter. Whereas in Bayesian inference, our focus is on estimating an entire parameter distribution based on the data. In frequentist inference, we assume that we don't know anything about the parameters ahead of time. We estimate them solely based on the data. Whereas in Bayesian inference, we explicitly incorporate our prior understanding or our lack of prior understanding. And in frequentist inference, any uncertainty about those parameter estimates, you can estimate it, but it's through indirect methods that involve various assumptions or asymptotic theory. Whereas in Bayesian inference, because you're working with the entire parameter distribution, uncertainty is really baked into the model. So, but one important point here is that if your prior expectations are weak, and you're mainly interested in parameter values, then frequentist and Bayesian methods are going to give you the same results. All right, so just a little bit more about what I mean by frequentist inference. So the main type of frequentist inference used is called maximum likelihood estimation. So basically, our goal is to find values for each parameter that maximize the likelihood of the data, or best explain the data is another way to put it. So that uses this likelihood function, which is also part of Bayes' rule, that represents the probability of the data given parameters. So in our simple linear regression example, now I've colored data and parameters consistently. This likelihood function for this example looks like this. I hope the colors help you see that it's just the same structure. You might notice here that so our data, particular y variable, is on a normal distribution with the mean as described by this line, and then the variance is described by some scatter. So again, it looks like this. And so the goal of maximum likelihood estimation is to find values for these three parameters that maximize this function with the observed x and y. So that's usually a mathematical optimization problem. A slightly more intuitive way to think about it is for the slope and intercept, an equivalent method is called ordinary least squares. So this is just finding the values for the slope and intercept that draw the best fit line between the points, specifically the line that minimizes the distance between the line and the points on the line. So this type of inference, at least with a simple model, is fairly easy to solve analytically. And even for more complex models, the computational methods aren't super expensive, memory-wise. All right, so on the other hand, Bayesian inference, our goal is a little bit different. Instead of finding the best parameter value to explain the data, we just want to update our understanding about the prior distributions based on the data. So here's Bayes' rule again. I hope this becomes intuitive to you. So this part is the likelihood of the data given parameters. That's what we are trying to maximize in maximum likelihood estimation. This term represents our prior understanding about parameters. So the probability of the parameter, regardless of the data or before seeing the data. This term represents our updated understanding about the parameters after seeing the data. So this is often called the posterior probability. And then this term on the bottom is just the support over plausible values of the data, which you can just think of as a normalizing constant. So the probability sums to one. We often kind of ignore this part in the theory. So expressed for the simple linear regression model, the Bayes rule just looks like this. So same thing, just putting our parameters and data in there. And our goal here is to just find an updated distribution function for these three parameters. So in order to do that, we first have to define some kind of prior distribution for our parameters. So that's usually going to be some kind of probability density function that is going to have a set of what I'm calling what is called hyperparameters. So these are usually values that represent, your level of expectation and certainty about your expectations. So the choice of priors comes from a combination of analytical convenience, what makes the model work, and most importantly, how they represent your prior knowledge or lack of knowledge about your system. Now, I want to comment about analytical convenience is that if you choose very, very specific priors, in theory, the posterior can be solved analytically without computer sampling. And people often say, like, oh, you have to have a computer to do Bayesian inference. Not technically. There are choices of parameters that will work, but and this is one example, but they don't make a lot of sense. In this case, it'll be solvable analytically if the uncertainty about what your slope and intercept are proportional to your uncertainty, your prediction uncertainty for the data. So that, if you think about that, it doesn't make a whole lot of sense. So if we make just one very small change in the direction of reality, so let's say instead of making those dependent, we make the hyperparameters independent of each other. With this tiny change, still a very simple model, the posterior now can no longer be solved without computer sampling. So this is along the lines of what people say when they say, oh, you have to have computers to do Bayesian stats. Okay, recapping. Statistical inference, Bayesian and otherwise, involves estimating unknown or unobservable parameters from observable data, such as estimating disease resistance from disease occurrence. Frequentist inference differs from Bayesian inference in that it focuses on parameter values instead of distributions. It estimates parameters solely from data. It's less well suited to dealing with uncertainty about parameters, but it's typically easier to perform and faster to compute. But frequentist and Bayesian estimates produce similar parameter estimates, like the values, when prior expectations are weak. And without computer sampling, Bayesian inference can only be performed on very simple models with very restricted priors. So here's a slide comparing some of the computation aspects of Bayesian versus frequentist, which I won't spend a lot of time on. But in next part, I'm going to talk about why computation makes Bayesian inference tractable and start to introduce some basic Bayesian computation methods.